Welcome to Understand Chemistry. This is Dr. Bilal. This is my fourth video in the series on free radical polymerization. In this video, we will understand the mechanism and kinetics of free radical polymerization. The first step of the mechanism of free radical polymerization is initiation. The initiation is subdivided into two steps: decomposition and the radical attack on the monomer to initiate polymerization. During the decomposition step, the initiator is decomposed into two radicals. For example, a benzoyl peroxide initiator is decomposed into two benzoyl radicals. The benzoyl radical is not stable and is converted to phenyl radical with elimination of carbon dioxide. The rate expression for the decomposition is described as the rate of change in concentration of initiator with respect to time, which is equal to the decomposition rate constant Kd multiplied by the concentration of initiator. This is the rate controlling step. In the chain initiation step, the free radical obtained from the decomposition attack the double bond of the monomer to initiate the polymerization. For example, the phenyl radical attack a styrene molecule to produce a styrene free radical. The rate expression for this initiation step is given by the rate of change in concentration of the Rm radical, which is equal to the initiation rate constant Ki multiplied by the concentration of the R radical and the concentration of the monomer. The overall rate of initiation is described by Ri is equal to 2fkdi. Now the question is, why do we have a factor of 2 in this equation? This is because each initiator molecule yields two radicals. F in this equation stands for initiator efficiency. Since not all radicals initiate polymerization, some are consumed in the side reactions. Details of these side reactions are comprehensively covered in my video on initiators for free radical polymerization. Due to side reactions, the value of F is not 1. Instead, it is found between 0.3 and 0.8. This reduction in the value of F due to side reaction is called the cage effect. During the propagation step, the styrene radical adds more monomer to the chain. For example, the styrene free radical attacks on styrene monomer with the rate constant Kp1 and then adds another monomer with the rate constant Kp2. This process continues this way. The rate of propagation is then described by the change in monomer concentration over time, which is equal to the propagation rate constant Kp multiplied by the concentration of the growing radical and concentration of the monomer. The rate of propagation is independent of the chain length. This means whether a radical adds more or fewer monomer, the rate will be the same. In the termination step, the macro radicals produced during the propagation step must terminate to produce a dead chain. There are several modes of termination. The first one is by combination or coupling. In this process, two propagating macro radicals combine to produce one dead polymer chain. The rate expression for termination by combination is represented by the termination by combination rate constant Ktc multiplied by the square of the concentration of the radical, and a factor of 2 accounts for the fact that each termination event eliminates two radicals. Termination may also take place by disproportionation. This process involves the chain transfer of a hydrogen atom from one chain to the free radical chain end of the other chain, resulting in two dead chains, one of which has an unsaturated chain end. The kinetic expression for termination by disproportionation is given by disproportionation rate constant Ktd multiplied by the square of the concentration of the radical, again with a factor of 2. The overall rate of termination is the sum of rate of termination by coupling and the rate of termination by disproportionation. Here Kt is the sum of rate constant for combination and disproportionation. Let us find an expression for the degree of polymerization for free radical polymerization, which is the total number of monomer units in a dead polymer chain. The degree of polymerization can be calculated in terms of kinetic chain length, which is the number of monomers consumed by each primary radical. Mathematically, kinetic chain length nu is equal to the rate of propagation over the rate of initiation, or the rate of propagation over the rate of termination if we use the steady state assumption that describes the rate of initiation equals the rate of termination. By placing the value of Rp and Rt, we get the following expression. Let us introduce a new constant K prime in place of Kp divided by 2Kt for sake of simplicity. By doing this, we get the final expression nu is equal to K prime into concentration of monomer divided by concentration of growing radical. This is equal to the degree of polymerization for termination by disproportionation. For termination by coupling, the degree of polymerization is equal to 2 times the kinetic chain length. The factor of 2 indicates that 2 kinetic chains are combined to produce one dead polymer chain. In the expression of kinetic chain length, the value of the concentration of the growing chain is difficult to determine experimentally. So, we replace it with an experimentally accessible term. We know that the rate of change in the growing chain concentration equal to the number of chains initiated minus the number of chains terminated. We use the steady state assumption, which states that the number of growing chain is approximately constant, so the rate of change is 0. Solving this for the concentration of the growing radical, we reach to the following expression. In this expression, we have to replace our radical. Again, we consider the steady state assumption for the primary radical. The rate of change in the concentration of the R radical is 0. This means 2F KDI minus KI R radical into concentration of M concentration of monomer is equal to 0. Solving this for the concentration of R radical, we reach to the following expression. Placing this value of R radical in the expression of M radical, we reach to the following expression. Now we use this value of M radical in the rate of propagation expression. After replacing the constant term with the constant K double prime, we get Rp is equal to K double prime concentration of monomer times the square root of concentration of initiator. Or we can say that the rate of propagation is proportional to the concentration of monomer times the square root of the concentration of the initiator. From this expression, we conclude that the rate of propagation increases linearly with monomer concentration. Secondly, the rate of propagation increases with the square root of the initiator concentration. Now let us place the value of M radical into the expression of the rate of termination. And on simplification, we get Rt is equal to 2FKD into I. According to this, the rate of termination is directly proportional to the concentration of initiator. Similarly, let us find an expression for the degree of polymerization without M radical term. By placing the value of M radical in the expression of degree of polymerization, and after replacing the constant term with another constant K triple prime, we get degree of polymerization is equal to K triple prime into M divided by square root of the initiator concentration. So we can see that the degree of polymerization is proportional to the ratio of the concentration of monomer to the square root of the concentration of initiator. From this equation, we can conclude that increasing the concentration of monomer leads to a higher degree of polymerization or longer chains, and increasing the concentration of initiator leads to a lower degree of polymerization or shorter chains. Let us discuss another form of termination, chain transfer, which also often leads to branching. In many polymerization systems, the final molar mass of the polymer is observed to be lower than expected based on coupling and disproportionation alone. This is due to the premature termination of the growing polymer chain by the transfer of a hydrogen or another atom to another species. such as monomer, initiator, or solvent. These displacement reactions are termed chain transfer reaction and can be described by the general equation as shown here. In this equation, XA is a chain transfer agent which could be a monomer, initiator, or solvent. In this reaction, the growing chain is terminated by one of the species with the formation of a new radical A that can start a new chain. Let us see some examples of how chain transfer reactions work for different species. In case of chain transfer to an initiator like AIBN, the growing chain is terminated by one of the radicals generated by AIBN, while the other radical adds to a monomer to initiate a new chain. Chain transfer to a monomer is also shown here. In this reaction, a proton is transferred from the monomer to the growing radical to terminate it, resulting in one free radical for further reaction. The same is the case for chain transfer to a solvent like toluene. In the case of chain transfer to a polymer, a hydrogen atom is migrated from the polymer to terminate the chain. As a result, a new radical is generated on the polymer chain and a polymer starts growing at that point. This type of chain transfer is called intermolecular chain transfer. Intermolecular chain transfer results in long chain branching, as the branching point can be quite far from the chain end. There is another way of chain transfer called intramolecular chain transfer. Here the radical at the end of the chain attack another part of the same chain. This is why this process is called backbiting. This results in short branching. The new radical site serves as branch point for adding chain extension or branching. The reason for short branching is that the chain end prefers a conformation resembling a stable hexagonal ring, as shown in this scheme. There are several possibilities for the radical to attack back on any carbon of the same chain. This results in different lengths of short branching as the polymer starts growing from the new site. Some of the possible branching patterns are shown in this scheme. If we also consider chain transfer as a termination step, then the number average degree of polymerization can be defined as the ratio of the rate of polymerization to the rate of all the reaction leading to dead polymer formation. Or mathematically, we can write this as shown here. In this equation, where in the denominator we have all the reactions leading to polymer formation, like termination by combination, by disproportionation, chain transfer to monomer, chain transfer to solvent, and chain transfer to initiator. To simplify the analysis, we often work with the reciprocal 1 over degree of polymerization. This let us break down the contribution of each process. Let's combine the termination by combination and disproportionation into RT. In the next step, let's divide each term separately by RP after placing the value of the concentration of the growing radical M radical that have previously found by steady state approximation, and on simplification we arrive to this expression where the first term corresponds to 1 over dPn naught, where the dPn naught is the degree of polymerization in the absence of chain transfer reactions. Let us introduce new constant Cm, Cs and Ci in place of the constant present in each term. By doing this, we ended up with this equation, which is called the Mayo-Walling equation. This is an extended form of the Mayo equation. For bulk polymerization, that is when no solvent is present, chain transfer to solvent is not possible. Then we can write the last equation as shown here. For a specific transfer agent Ta, the Mayo-Walling equation can be written as shown here. This is an equation of straight line. A plot of 1 over dPn versus Ta over m yield a line with a slope equal to the chain transfer constant. In the table, the value of various kinetic parameters such as concentration, rate and rate constants involved in the photopolymerization of methacrylamide, as well as the range of values generally encountered in radical polymerization are given. In this table, we can see that the Kp value is approximately 10 raised to power 3, which is much greater than that for the esterification, urethane and phenol formaldehyde polymerization, where this value is 10 raised to power minus 3, minus 2 and minus 6 respectively. This means that in radical polymerization, propagation is very fast and we achieve high molar mass polymer instantaneously. The termination rate constant is about 10 to the power 7, which results in quick termination. This means radicals have low concentration, something like 10 to the power minus 8 mole, or radicals have a very short lifetime. For example, for methacrylamide, the lifetime of radical is 2.62 seconds. The rate of initiation found experimentally was 8.75 10 to the power minus 9, which is in great agreement with the calculated value of 8.73 into 10 to the power minus 9. This validates our steady state assumption. Let us talk about the molar mass distribution of radical polymerization. The molar mass distribution of free radical polymerization is complicated as it involves different modes of chain termination like coupling, disproportionation, and chain transfer reaction of several types. In addition to this, the molar mass of polymer varies at any instant with the overall percent conversion. For low conversion polymerization, the kinetic parameters such as the concentration of monomer and initiator, the rate constant for decomposition, and other rate constants have constant values. Under these conditions, the molar mass of polymer does not change significantly with conversion. This statement can be confusing. Actually, conversion means more monomer are added to the system. So polymer molar mass should increase. Remember, here we are talking about very low conversion. For example, 10 to 15%, where initiation and propagation dominate and few chain terminate. This results in little change in the average molar mass of the chains. Let us consider the case when one polymer molecule is produced from each kinetic chain. This means termination by disproportionation or chain transfer or combination of both. But for this case, we assume no coupling reaction. For this case, the molar mass distribution is described by the statistic of linear chain. The number average and weight average degree of polymerization for this case are given here. From these, we can calculate the number and weight average molar masses. The dispersity is calculated by dividing the weight average degree of polymerization by the number average degree of polymerization, which is calculated to be 1 plus P. This is the same equation as we found for step growth polymerization. The difference in the use of this equation for radical chain polymerization compared to the step growth polymerization is the redefinition of P. Here, P is the probability that a propagating radical will continue to propagate rather than terminate. The value of P of this reaction is defined as the ratio of the rate of propagation to the sum of the rate of propagation and the rate of termination by disproportionation or chain transfer. The expression for dispersity indicates that for high polymer, where the number and weight average degree of polymerization is large, the dispersity approaches 2. This is possible when P approaches 1. This occurs when the rate of propagation is much greater than the rate of termination. Now consider the case when the termination happens only by coupling. This means two kinetic chains lead to one dead polymer molecule. Coupling results in a relatively narrow size distribution. The case resembles step growth polymerization with branching. The number average and weight average degree of polymerization for this case are calculated as shown in these equations. The corresponding molar masses can be calculated from the following equation. From the weight average and the number average degree of polymerization, the dispersity is calculated to be 2 plus P over 2. For high conversion, when P approaches 1, the dispersity for the case of coupling is calculated as 1.5, which is less than the dispersity calculated for the case of disproportionation and chain transfer, which was 2. Let us see the cases for high conversion polymerization and dispersity. For high conversion polymerization, the size distribution is much broader. The concentration of initiator and monomer decrease during polymerization, and the molar mass of the polymer is proportional to the ratio of the concentration of monomer to the square root of the concentration of initiator. Normally, the initiator concentration decreases much faster than the concentration of the monomer. Therefore, the molar mass of the polymer increases with conversion. The value of dispersity for such high polymer typically ranges between 2 and 5. R2 acceleration, also called Thomsdorf-Nourish effect or gel effect, is a phenomena observed in free radical polymerization, especially in bulk or solventless polymerization, where the rate of polymerization suddenly increases after a certain point in the reaction. This is accompanied by an increase in the ratio of the propagation rate constant to the square root of the termination rate constant. This results in large molar mass with a broad distribution. The value of dispersity for this case ranges between 5 and 10. Chain transfer to polymer can lead to dispersities of 20 to 50. Such high broadening occurs because chain transfer to polymer leads to branching, and branching leads to more branching. Chain transfer can also lead to an increase in molar mass. This is all about the kinetics and mechanism of free radical polymerization. In my next video, I will discuss the thermodynamics of polymerization. Thanks for watching.